last lecture, we described towed streamer seismics, including the notion of seismic events. We will now discuss cross-sections of seismic data, including shot and receiver gathers, midpoint and offset gathers. We will also discuss out-of-plane reflections and swell noise. As described earlier, the towed streamer experiment consists of setting off a bang, which is the source, in the water, letting the wave field bounce through the subsurface, and recording the time it takes to bounce back to the sea surface, which is at the receiver. Then the source location is moved to a specified distance, and the process is repeated. Seismic boats generally move at 5 knots, which is about 20 seconds per 50 meters. Many receivers are used to record returning signals from each source location. Each receiver recording is called a trace, and the group of traces corresponding to the same seismic source is known as a shot gather. So a shot gather is a side-by-side display of seismic traces which have the same shot point coordinates. Let's repeat this due to its importance. Many receivers are used to record returning signals for each source location. Each receiver recording is called a trace, and the group of traces corresponding to the same seismic source is known as a shot gather. So a shot gather is a side-by-side display of seismic traces which have the same shot point coordinates. If we denote by xs the source position vector and by xr the receiver position vector, the pressure wave field can be written as a function of source position vector, receiver position vector, and time. The time variable here is the travel time from the source to the receiver location. Pressure wave field P is a scalar function because pressure is a non-directional quantity. In some towed streamer experiments, the receiver and source depths Zs and Zr are allowed to vary during the survey. We assume that the data are gathered along a straight line with constant depth Zs for the sources and constant depth Zr for the receivers. A point on this seismic line is selected as the origin so that Ys equals Yr equals 0. Hence, we need only to consider the subspace T, Xs, Xr, in which the wave field is a function of only 3 variables, again T, Xs, Xr. A seismic signal can be defined as a measurement of displacement or pressure variations with respect to time and/or space. Many receivers are used to record returning signals for each source location. Let's repeat this. A seismic signal can be defined as a measurement of displacement or pressure variations with respect to time and/or space. Many receivers are used to record returning signals for each source location. Each receiver recording is called a trace. Each trace is defined by a source and a receiver. It describes pressure variations with time for a pair of one source and one receiver. Traces corresponding to the same shot point represent a shot gather. So a shot gather is a side-by-side display of seismic traces which have the same shot point coordinates. In other words, shot gathers are the time and receiving cross-sections of the pressure wave field. Each cross-section corresponds to a limited experiment with one shot and all receivers available. Similarly, we can introduce the time and sources cross-section known as a common receiver gather. The pressure wave field in this cross-section corresponds to an experiment with all shots recorded at a single receiver. Note that pressure wave field P is a scalar function, because again, pressure is a non-directional quantity in this case. Notice also that in some towed streamer experiments, the receiver and source depths ZS and ZR are allowed to vary during the survey. The left-hand figure illustrates the concept of shot gathers, and the right-hand figure illustrates a receiver gather from the Pluto 1.5 described in the previous lecture. We can see that common receiver gathers and shot gathers are quite similar in an experiment in which source and receiver positions can be interchanged based on the reciprocity theorem, as in the towed streamer experiment. The reciprocity theorem is an assertion about a single experiment carried out twice with an exchange of source and receiver positions. That is as follows. For reciprocity to be valid for the ensemble of all shots and receivers along the seismic line, it is necessary that depths ZS and ZR be equal. In the case in which ZS equals ZR, an important consequence of the reciprocity theorem is that the wave field generated by a source at XA for receivers along X equals the wave field recorded at XA for individual sources along X. That is, as follows. For all of X. In other words, a common receiver gather at XA is equal to the common shot gather at the same point, XA. Here we discuss the applicability of the reciprocity theorem in a towed streamer experiment, in which the source and receiver depths are constant. We consider two similar experiments, in which the coordinates of sources and receivers along the x-axis in one experiment are exchanged in the other experiment, drawing not to scale. In experiment number 1, the sources and receivers are in blue. In experiment number 2, the sources and receivers are in red. The difference between the source depth and receiver depth is denoted by delta Z. We now compare data corresponding to the two experiments for the case in which delta Z equals 0 meters. That is, source depth equals receiver depth. The trace in blue corresponds to the first experiment, and the trace in red corresponds to the second experiment. The difference between the two traces is zero trace. This result confirms that reciprocity theorem applies in this case. We now compare data corresponding to the two experiments for delta Z equals 5 meters. Notice also that the traces of the two experiments are very similar in regards to the arrivals of various events and the shape of the waveforms. However, even one sample shift is enough to produce large differences in the two experiments, because the arrivals of various events and the shape of the waveforms are almost identical. We generally assume that reciprocity is valid in such a small delta Z. Notice that the direct wave and its ghost, that is, the first two events, are identical in the two experiments, irrespective of the value of delta Z, because their wave paths are not affected by the lateral heterogeneity of the corner diffraction. That is why the difference between the two traces are 0 for some events. We now compare data corresponding to the two experiments for delta Z equals 25 meters. The difference between the two traces are now large. This result confirms that reciprocity theorem does not apply in this case. An illustration of the applicability of the reciprocity theorem in a towed streamer experiment in which the source and receiver depths are constant. Here we show seismic trace, source and receiver pair positions in a 2D survey of towed streamer data. Rows are shot locations, and columns are receiver locations. In practice, the requirement that ZS equals ZR is frequently ignored for towed streamer data because the distance, delta Z, is less than 5 meters. The filled squares are recorded traces, and the empty squares are deduced from recorded traces by reciprocity. Now that we have introduced reciprocity, we are ready to describe midpoint and offset gathers. Although seismic data are naturally recorded in the form of shot gathers, they are sometimes reorganized in other domains in which processing may be physically more intuitive or for which some of the important features in seismic data reveal themselves more clearly than in shot gathers. The common midpoint gathers and common offset gathers constitute an example of such a domain. The distance between the source and receiver for a given shot gather is called the offset. A near offset is the distance between the source and the nearest receiver to the source for a given shot gather, whereas a far offset is the distance between the source and the farthest receiver to the source for a given shot gather. We can also describe the pressure wave field in terms of the midpoint vector and the half offset vector. Here are the definitions of midpoint and half offset vectors. Note that these are linear coordinate transformations of source position and receiver position vectors. In this geometrical diagram, we show all 4 of these vectors, that is, midpoint, half offset, source position, and receiver position vectors, for the particular case in which source and receiver depths are 0. This geometrical diagram also holds when the source and receiver depth are constant and equal. To better understand this change, let's limit our discussion to the collection of multiple coverage data gathered for a single seismic line. We will assume that the data are gathered along a straight line with constant depth ZS for the sources and constant depth ZR for the receivers. That is the meaning of a single line acquisition, often called 2D acquisition. A point on this seismic line is selected as the origin so that YS equals YR equals 0. Hence, we need only to consider the subspace T, XS, and XR, in which the wave field is a function of only 3 variables. Here we are showing the data description in source, receivers, and time for a single straight line acquisition. On the left, we have data in source-receiver domain. On the right, we have data in the midpoint offset domain. The common midpoint or CMP gather is the time and offset cross-section. The left figure shows the experiment corresponding to a CMP gather. The variable in the CMP gather is the distance between the source and receiver, called the offset. Again, a near offset is the distance between the source and the nearest receiver, whereas a far offset is the distance between the source and the farthest receiver. Similarly, we can introduce the time and midpoints cross-section known as the common offset gather. The pressure wavefield in this cross-section corresponds to an experiment with all shots recorded at a single offset. Notice that when the medium is one-dimensional, that is, all the interfaces between rock formations are horizontally flat, the midpoints coincide with the reflection points. However, we can see here that for dipping interfaces, the reflection points no longer coincide with the midpoints. These figures show common midpoint and offset gathers from the Pluto 1.5 dimension dataset discussed earlier. Notice that from the 4 cross-sections introduced so far, the common offset gathers give the best indication of the shape of the model of the subsurface. Reciprocity also applies in the CMP domain, assuming that the source depth is equal to the receiver depth. Here is the reciprocity formula in CMP domain. The equation in blue shows that CMP gathers are symmetric with respect to zero offset. This figure provides another useful way to look at the 4 cross-sections of seismic data that we have just introduced. Again, this figure is limited to the case in which YS equals YR equals 0. That is a straight line or 2D line acquisition as we introduced in the previous slide. This display of source and receivers is generally known as a shot diagram. Notice that a seismic survey is described as a matrix form in which the rows correspond to common shot gathers and the columns to common receiver gathers. The diagonal is the zero offset sections, and all the other lines parallel to the diagonal are common offset gathers, also known as common offset sections. The lines perpendicular to the diagonal are the CMP gathers. Let's now talk about a feature which has made seismics a central component of the EMP industry. That is the ability to take into account out-of-plane reflections in seismic acquisition imaging. In the past, seismic data consisted of single inline acquisition, known as 2D seismics. The model of the Earth in this acquisition and in the subsequent seismic imaging process is assumed to be invariant along the crosslines. This, of course, is not true. Because of the structural features of the sea bottom or other reflectors below the sea bottom, reflected events from outside the vertical plane will be recorded in the 2D data. When the source is fired, seismic energy propagates outward in an expanding wavefront. In the absence of any variation of the geologic structure with the vertical plane of the 2D acquisition line, only reflections returning from within the vertical plane would be recorded. If, however, there were a structural feature, such as the scattering points outside the acquisition plane, out-of-plane reflections from these scattering points would also be recorded. The presence of reflections from out of the plane is one of the inherent problems with 2D seismic data. It is usually difficult to distinguish reflection events from within the vertical plane of the 2D seismic line from out-of-plane reflections. If these reflections are ignored in our imaging schemes, we can end up with inaccurate representations of the subsurface. Notice that out-of-plane reflections occur as primaries as well as multiples. Marine data acquisition, as depicted here, is known as multi-source and multi-streamer, also called MS/MS acquisition. Actually, 3D marine data acquisition became affordable in the 1990s, due in large part to the high productivity of multi-streamer acquisition technology. Multi-streamer acquisition generally corresponds to a boat towing 2 sources and 8 streamers, or 16 streamers with a streamer spacing of between 50 meters and 100 meters. The sources are fired alternatively in flip-flop every 25 meters. That is, each individual source is fired every 50 meters. The spacing between shot points in one shooting line is 50 meters, and the sail line spacing varies between 200 meters and 800 meters. Here we illustrate a typical sailing path of a 3D survey. Again, only the shooting lines are shown here, not the streamers. The vessel travels back and forth, shooting and collecting data along many parallel lines, resulting in seismic data generated along lines 25 to 50 meters apart. Note that it takes about 9 hours to turn from one sailing line to another for a vessel carrying 10-kilometer long streamers. If we follow the yellow line, for example, note that when we finish one line, the next line is more than 10 kilometers away from the previous line because of the complexity of turning such a long vessel or streamer. Note also that in general, during the time of turning from one line to the other, we do not collect data. Efforts to collect data during the turning of the sailing line are being made to optimize the acquisition time, but the resulting data are generally still very noisy. Here is an example of data selected during the turning of the sailing vessel. Indeed, you can say that they are very noisy. Let's now talk about a swell noise, which is the key parameters for stopping seismic surveys. Noise in seismic data can be defined as a signal that our mathematical model cannot account for. In marine acquisition, noise can be created by side effects related to the seismic source detonation or can emanate from sources other than the seismic survey. For example, electrical power lines, ship props, drilling, other seismic boats, and wind or rough seas. Rough seas are the most important source of noise in marine acquisition. This noise is called swell noise. It corresponds to ocean swells during rough weather. The level of swell noise is actually the principal factor determining the acceptability of marine seismic data in rough weather. The left figure here shows a shot gather from the Atlantic Ocean, west of the Shetland Islands, affected by swell noise. The data quality is such that in normal circumstances, that is, in conventional seismic data acquisition, the data would be rejected and the acquisition will stop. So the data shown here were recorded for the goal of investigating characteristics of swell noise, but not for use in conventional seismic imaging. Swell noise occurs predominantly at low frequencies, below 20 Hz. However, in extreme sea conditions, it can be present above 20 Hz. The swell noise above 20 Hz is generally known as breakout noise because it is due to a hydrophone either breaking out from the sea to the atmosphere or being close to breaking out. In other words, the hydrophone stops recording the change of pressure in the water and now will measure the change of pressure in the atmosphere, which is undesirable in this case. The figure on the right shows an example of breakout noise. Because of variations in the sea surface, a hydrophone can experience recording in the water, which is the desired recording, and recording in the air, which is undesirable. That is breakout noise during the recording times. The standard technique for removing swell noise from our data is to apply a high-pass filter to the data. The right-hand figure here shows the same data as in the left-hand figure, but with high-pass filtered at 20 Hz. we can see that a significant amount of swell noise has been reduced, and the hydrophones with breakout noise are also more clearly visible. One of the major drawbacks to this technique is that it reduces the bandwidth of the seismic signal. Advanced methods for reducing swell noise have been developed and are discussed in future lectures. An alternative approach to avoid recording swell noise during the towed streamer acquisition is to tow streamers as deep as physically possible. By doing so, we reduce the exposure of recording sensors to the sea surface harsh environment, and therefore we reduce data and consequently acquisition downtime. However, the effect of receiver ghosts on seismic data becomes increasingly severe as streamer depth increases. The conventional data processing practice of treating receiver ghosts as a part of an effective source signature, which includes the effect of the ghost, does not hold. The dual sensor recording technology discussed in the next lecture provides a way of eliminating the receiver ghost from the data in this case. Note also that the towed streamer technology is used in icy Arctic waters. Because of the harsh near-sea surface environments in this case, deep towing is the common solution. Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of wave propagation, elasticity, electromagnetism, wavefield sampling, wavefield decomposition, and imaging. Thank you for listening to this iMode education lecture.